Buffers. Buffers are defined as a solution characterized by the ability to resist changes in pH when limited amounts of acid or base are added to it. So examples of a buffer would be a weak acid and its conjugate base, or a weak base and its conjugate acid. So it's really important that you understand this other definition of a buffer, that if you do have a buffer system, it would be composed of a weak acid and its conjugate base, or a buffer system could be composed of a weak base and its conjugate acid. So let's look at a problem. We have a problem in which we have 0.50 molar acetic acid and 0.50 molar sodium acetate. So when we set up our ice table, we have acetic acid in equilibrium with hydrogen ion and acetate. So remember here, for the hydrogen ion, you don't have any to begin with. So we would want to take the molarity of our acetic acid from the problem and put it in for our initial molarity of acetic acid here. And then we would want to take the molarity of the acetate and put it in for our initial molarity here. And remember, the sodium is a spectator ion, so we will ignore it. So we have our initial, we consider the forward reaction. So we would have for our change minus x plus x plus x. For the equilibrium, we would have 0.50 minus x for acetic acid, x for our hydrogen ion, 0.50 plus x for the acetate. So we're going to set up our K expression, and we would have the acetic acid Ka that was not given, but we know what it is because we've used it so much. So here's the Ka for acetic acid, 1.7 times 10 to the minus 5. And then we would set up our equilibrium for the H plus with X. So our table says the equilibrium for the acetate was 0.50 plus X. We put that in. And then the equilibrium for the acetic acid was 0.50 minus X. We put that in. So if we use the 5% rule, we can assume this X is small, assume this X is small, and then we would simplify the equation. And so this expression is equal to the Ka. We solve for X. We get our X. It's the hydrogen ion concentration. And so we put that into our pH expression and we get the pH. So this is the pH for our system in which we have 0.5 molar acetic acid and 0.5 molar sodium acetate. So what we're going to do now is use the same system, and we're going to add some sodium hydroxide to our system. So when we set up the table here, we are taking into consideration that sodium hydroxide is a strong base. And so we are reacting the sodium hydroxide with the acetic acid. So the reaction goes this way. So we have this much molarity of our acetic acid from the prior problem. We have, this is our molarity of the hydroxide, and remember we had some acetate also. The change in this case is a limiting reagent type problem. Since hydroxide is our limiting reagent, we will subtract it from the hydroxide, and that's how we get the 0. We subtract it from the acetic acid, so that's how we get the 0.49. But because we are going this way, we're adding it to the acetate, so we get the 0.51. So once you have your final here, this final is what you're going to use to put into your ice table. So this was our final concentration of acetic acid. So that's where we get the value here. We have 0 of the hydrogen ion. And then this was the value of the acetate we had from our table. We put that in here. So you will first have to do a table to react the base. This is a strong base with the weak acid. And this is a limiting reagent table. So once you have the limiting reagent table and you set up your ice table, then you do the reactions just like we've been doing before. So here we have our initial. We're going to consider the forward reaction. So minus x plus x plus x. We have our equilibrium values here. And so we put our products over reactants. So this would be our Ka expression here. And then this is our hydrogen ion. So that went in here. This was our acetate. So that went in here. And then this is our acetic acid, and that went in here. So what we're going to do is assume x is small, assume x is small, and so that simplifies our equation. And then what we can do is we can solve for x. And remember that our x is our hydrogen ion. And so when we get the x, we can put it in our pH expression, which I did without showing you. And so we solved for pH. So we had a pH of 0.479 when we added the buffer. So if we look at, okay. Oh, I can do this guy. Maybe not. Okay. So if we look at the, this keeps moving down too far. Okay, so if we look at the pH of our buffer system, then we can compare it to the pH we had before. So the pH we had before was 4.76955. That was before we added sodium hydroxide. So now we have a pH of 4.79, so it did not change very much. So yes, this is a buffer system. So this is an example of a buffer question. We had to do a limiting reagent table first before we could use our ice table. And then once we get the ice table, we just can solve it the way we've been solving it this entire time.